Okay, so I'm going to talk more about Fehling's test and Tollen's test, and this is definitely an extension thing, and it's what we're going to draw together a few different ideas, and I've written them up here. Okay, so we're just back to being blue, right? So we'll talk a bit about equilibria here. Okay, we're also going to talk number 2, or I should put down there. We're going to talk more about redox in inorganic chemistry and oxidation numbers and stuff like that, balancing half equations and so on. And then these other 2 points, 3 and 4, I'm going to talk about them at the end. Then you might want to switch off if you're still in year 12 because you haven't done about complex ions and insoluble metal hydroxides. But if you're revising this and you're in year 13, you will understand about that. Even if you haven't covered complex ions, I'll try and make it so that it does make sense. But it is there's a few quite interesting points here. Okay, so let's have a think about Fehling's test first of all. Fehling's test, we know, is they're copper 2+ ions, okay? And they get reduced to copper 1 oxide. So let's balance that half equation. I need to put a 2 there. And then I need to put an H2O here. And then I need to balance for hydrogens. I need to put 2 hydrogens on that side of the 2 H pluses there. And then in terms of charges, well, I've got 4+ on this side, okay, and I've only got 2+ on this side. So I need to put in 2 electrons in there, don't I? Okay, I'll put them in blue. Plus 2 electrons, okay. And if you want to check that, the oxidation number of copper there is +2, and here it's only +1. So it's been reduced by 1 electron's worth. Why do we need 2 electrons? It's because there's 2 copper atoms. So that's all good. Right, let's have a look at the organic half equation there. Well, we're oxidizing, let's say we've got ethanol, sorry. So we've got CH3CHO, that's how we write an aldehyde on one line. And if you remember, that's going to get oxidized by the Fehlings. Fehlings gets reduced, this aldehyde gets oxidized to a carboxylic acid. Right, so let's balance that half equation. So we're going to need an H2O on this side of the equation, the oxygen. Then we have got 4, 6, so we need 2 H pluses on this side. And to balance that, we need the charges, we need 2 electrons. So what I'm going to do is going to combine those 2 equations into a full equation. Which is quite easy because there's 2 electrons there and 2 electrons there, so we don't need to do any multiplying. So we're going to get 2Cu2 plus the aldehyde plus that water and that water, so the 2 H2Os is going to give us copper 2 oxide and ethanoic acid. And then we need those 2 protons, and those 2 protons is going to be 4H plus. Now, so this is the reaction that's going to happen. Now, this is actually an equilibrium reaction. So if I just rub out that, okay, and it's an equilibrium reaction, and it lies over to the left, okay, and it doesn't really work, okay. So because it's so far over to the left, it all just stays as copper 2 plus, and it won't convert to copper 1 oxide. It doesn't work. So what can we do to push this equilibrium to the right? What can we do? Well, the clue is here. Is you've got a load of you make a load of H plus ions, okay? So if we can keep removing them, the equilibrium, Flusha-Tellier tells us, is going to move over to the right to try and make some more. Okay, and so we will get the copper oxide produced. We'll push, make the reaction happen. So how can we keep removing H plus? Well, the best way of doing that is, of course, is to add alkali. So we have seen there from that equilibrium, so this reaction okay, will only occur, so the reaction will only occur in alkaline solution. It won't happen at neutral. It won't happen in acidic conditions. So what can we do? Well, you might think, so what can we do? Well, can we add some sodium hydroxide? That will make it alkaline, wouldn't it? Unfortunately, you can't do that because copper 2 plus will react with hydroxide ions to form a precipitate of copper hydroxide. Okay, so that won't work. So you have to be a little bit more subtle than that. And the way you make it alkaline is by without precipitating out the copper 2 plus ions, is you add a ligand. And this is the bit you won't understand if you're not in year 13. We add a ligand to complex with the copper 2 plus ion, and that ligand is the tartrate ion. Okay, right. Okay, now the tartrate. I can't read that properly. That's not a proper proper name, is it? So that's its common name. Just draw out what does the tartrate ion look like? Well, the tartrate ion looks like this. It is butane dioic acid. It's a salt of butane dioic acid. So yeah, and it's also got a couple of hydroxides on those carbons there. Okay, that is that's tartrate. And if you probably realize, right, the lone pairs of electrons that you've got here, these form dated bonds with these form dated bonds with the copper 2 plus ions, yeah, forming a complex, and that keeps it soluble. Also, because again this is a little bit more year 13, so because tartrate, this is a salt of a weak acid. Now, salts of weak acids are always solutions of them are always slightly alkaline, because if it's a weak acid, it means that this is a fairly good base. Okay, so that's how you keep the solution alkaline, and you stop without the copper 2 plus ions precipitating out. You've got to keep the solution alkaline because, yeah, to push the equilibrium forward to use up those H plus ions. Okay, now let's do if you can bear to carry on watching, let's do what happens with Tollen's test. It's a very similar story. Okay, I think I'll clear that screen actually. Right, so Tollen's test, right, what's happening there? Tollen's test, you've got Ag plus in solution, yeah, and that forms a silver mirror, doesn't it? It forms the silver solid. So what do we need to do to balance that half equation? Easy, no oxygens or hydrogens to worry about, just put an electron in there. Then we had the let's see, the aldehyde one we had before, didn't we? So I won't. I think it was H2O, and it gave you the carboxylic acid and 2H plus. And 2 electrons. So what can we do? We've got to combine those. So this is the oxidizing agent, isn't it? Silver plus, because it gets reduced to Ag. This is the reducing agent because it gets oxidized. Combine these two together. I need to multiply the silver one by 2 because there's only 1 electron there. We've got 2 there. Let's write that. So we end up with Ag, let's say 2Ag plus, plus CH3, CHO, plus water, goes to 2 Ags, plus ethanoic acid, and 2H plus. Okay, again, this is an equilibrium reaction, so I'm going to rub that out and put an equilibrium arrow in there. Le Chatelier tells us, again, how can we push the equilibrium to the right? How can we do that? How do we do that? We do that by adding, so removing the remove the H plus ions. How do you remove the H plus ions? You make the solution alkaline. And once more, you can't just add NaOH, because if you do, you will get a precipitate of silver hydroxide. So that's not going to work. So what you have to do, I don't need any brackets there, do I? There's only one. Get a precipitate of silver hydroxide. So how do you make it? How do you make it alkaline? Well, you add you add ammonia. Okay, so that's why Tollen's reagent is sometimes called ammoniacal silver nitrate solution, isn't it? You add ammonia to silver nitrate. Well, why do you add the ammonia? That's going to make it alkaline. And it is also, in year 13s, it's a ligand. Okay, it will form a complex. So you've got the lone pair on the ammonia. It will complex with the silver ion and keep it soluble. And that's why you can't just add silver nitrate. You have to use ammoniacal silver nitrate to make it alkaline, push the equilibrium in the right direction. So there's a whole load of sort of synoptic things going on in that. But if you're in year 12, it's a bit over the top. Right.